Hello and welcome to Easy as Pie with Mr. Carpenter. I am Mr. Carpenter, and I wanted to make sure that we had the right footing with the normal distribution because a lot of us were not here, and also a lot of us left early, and I just don't feel like we were at the level of understanding that I really want us to be at. So I just wanted to make an extra resource for you. So just an overview of the normal distribution, right? So I collect a set of data, right? And let's say I make a dot plot for it. And if my dot plot looks kind of something like this, where all the data seems to be bunched in towards the middle at a very high frequency, but then kind of is very rare to have data points spread out further, then we make what's called a bell curve or a normal distribution. It's a very popular distribution. If you look on Teams, you'll see some very popular examples of normal distributions, including my favorite one, the Galton board, also known as the Plinko board, is a very cool example of a normal distribution. So what does it mean for us? Well, you'll see these percentages here. So right at 0, we have the mean. So this is the average of the data right here. So that's going to be the centermost of the data, and that's going to represent the most popular answer, the popular data point, because it's the mean, it's the average, right? And then these numbers over here represent the standard deviation, right? And so the example that I use is the heights of males, heights of boys, right? And if you're one standard, right, the average height of a male is, I believe, 5'6", which would be 5'9", sorry, 5'9". Right, so someone who's only one standard deviation away from the mean is going to be pretty close to 5'9", right? So this is everyone who's within one standard deviation of the mean, pretty close to 5'9", right? And then you have very few people who are like NBA basketball players that are like 7'7" or 6'8", right? That they are rare, right? So they're going to represent this part of the bell curve. They're more standard deviations away from the mean, right? And they're much less likely to occur, right? Same thing over here. This would be like a 4'11" dude, which is not as common as the average, which would be 5'6", 5'7", right? And thankfully, we have this the questions that you'll see today do rely on the intricacies of this chart itself, but we have this rule called the 68, 95, 99.7 rule, right? And then 68% of the data falls between one standard deviation of the mean, right? And if you add up these, right, because these percentages right here represent all the data that's either one standard deviation more than or one standard deviation less than the mean. If you add them up, you get like 68.2, which we round down to 68%. 95% of the data falls between two standard deviations. So if I go here and here, all this data adds up to around 95%. And then 99.7%, my apologies, falls between three standard deviations of the mean. So a vast majority of the people are going to fall within three standard deviations of the mean, right? And if you're not, then you're part of the 0.3% that's very rarely either unusually high or unusually low in terms of your data point. And if we know that a data set is normally distributed, we can use that along with this chart to help us glean information from it. So I'm going to erase this and this because we're going to be using this chart frequently as we tackle a couple of these problems. So let's start with this one. So number 3. If 1 quart bottles of apple juice have weights that are normally distributed with a mean of 64 ounces and a standard deviation of 3 ounces. So now once I see those, right, I can fill in my normal distribution. So I have a mean of 64. So we'll go here, right? That will be 64. That's the mean. And then I look at the standard deviation, and that's going to be 3 ounces. So if I go one standard deviation above the mean, right, it would increase by 30 ounces, so it'll go up to 67. If I go up 2 standard deviations, it'd be 70. 73, right? And that can go lower as well. So you have 61 ounces, 58 ounces, 55 ounces, right? And now what I have is a normal distribution filled out that I can pick up information from. For example, 68% of apple juices are going to be within 61 to 67 ounces. 95% of apple juices are going to be within 58 and 70 ounces. 99.7% of apple juices will be between 55 and 73 ounces, right? For the purposes of any quiz or exam, that is the most that I will expect you to know of the normal distribution. But once again, these questions are going to get a little deeper, which is good. So, what percentage of bottles would be expected to have less than 58 ounces? Okay, so where does 58 show up on my standard deviation? That'll be right here. And it's all the stuff that's less than 58. So the percentage of this portion of the curve here, which is, we got 1.7 plus 0.5 plus 0.1, right? So just these portions as well that are all filled in. And that would be 2.3%. And let's see if that's one of my answer choices. It is. It says number 4, 2.3% of apple juice quarts bottles less than 58 ounces. So let's apply this and take it to number 4. Historically, daily high temperatures in July in Red Hook, New York are going to be normally distributed with a mean of 84 degrees Fahrenheit and a standard deviation of 4 degrees Fahrenheit. So you have a mean of 84, a standard deviation of 4. So now we can fill this in with new numbers. So 84, standard deviation of 4. So we got 88, 92. Once again, standard deviation is 4 degrees. So if I go up one standard deviation, I'm going to go up 4 degrees. 96 degrees. Then I can go down 80 degrees, 76 degrees, 72 degrees. And let's look. How many of the 31 days of July can a person expect to have temperatures above 90 degrees? Okay. First of all, let's find out what percentage of days are going to be above 90 degrees. So where does 90 degrees show up here? Well, it's not exactly within a rigid standard deviation, right? If 88, I go up 4 to get to 92, then 1.5 standard deviations, I'll go up by 2, and that'll bring me in 90 degrees. So half a standard deviation, so half of 4, which is 2. So these are all the days that are going to be greater than 90 degrees. So what percentage is that? Okay, well, we have 4.4 plus 1.7 plus 0.5 plus 0.1. Don't feel like doing mental math because great mathematicians are lazy. So 4.4 plus 1.7 plus 0.5 plus 0.1. 6%. 6% of the days are going to be 90. Now, that is an answer. Not the right answer, though, because I want a physical number here. I want to know how many of the 31 days. So I need to know what 6% of 31 is. Okay, well, I need this to be converted to a decimal. So 0.06 times 31. And if you multiply that out in your calculator, you get 1.86, which is around 2 days. So now I know there's probably going to be, I could expect 2 days of above 90 degree weather in July, which is pretty good because it's not like 103, which is very hot. Let's do one more. Recent statewide math test, raw score average, the mean, was 56 with a standard deviation of 18. So that's a pretty large standard deviation, which kind of tells me that there's a wide spread of scores here. We have students that did really well, and we have students that did very poorly. So 56, standard deviation was 18. So we go up one standard deviation to get to 74. It's 92, 110, and then 38, 22. Okay. Where is it? Here it is. What percentage of students scored below a 38 on a test? Well, where is 38 on my normal distribution? It is right here. So that's everyone who got worse than a 38 on the test. So we have 9.2 plus 4.4 plus 1.7 plus 0.5 plus 0.1. Which is 15.9% of students. So I can go ahead and fill that. So how many students scored less than the 38? Well, we need to know what 15.9% of 24,000 is. Convert this to a decimal, which of course, if you don't know the trick, you're just dividing by 100. So 15.9 divided by 100 is 0.159 times 24,000 equals 3,816 students scored less than the 38 on this test. And I think that's enough examples for you to have a pretty solid understanding of the normal distribution. Let me know if you have any questions.